So my talk, I decided to go with a very mysterious, kind of quirky title, Black Boxes and Unicorns. What it's about is black boxes I'm referring to kind of complex machine learning models. And unicorns I'm referring to data scientists, right? Because they're unicorns. Now, I didn't coordinate this with Josh, but like a lot of my stuff piggybacks very well off of Josh's talk earlier, and so I'll probably focus a lot more on the black box, and I may not have enough time to get to the unicorn part, but let's see if I can squeeze them both in. Well, so who am I? So really quick, I was a applied data scientist working at an insurance company for about 8 years. I like tools like R, Python. Long walks on the beach. I like SAS. I used to use SAS, but I put the logo, it's upside down on purpose because I'm not that proud of it. I've done pretty well in Kaggle, won some competitions, and I think I'm still ranked pretty high. The company has been around for 3 years. So whenever I'm watching one of these talks, what I'm doing right about this time is like Googling the company on Crunchbase. So I figured I'd just like do it for you. So we've raised a bunch of money. We have over 120 employees spread across the world. Some of the interesting employees, it would be like, I guess what we're kind of famous for is having like really good Kagglers in our company. How many of you have heard of DataRobot? We try to stay like really quiet, so that's good. So the people who do know us, they know us for some of the data scientists on our team. Have been atop the Kaggle rankings for a long time. Basically, over the last 3 years, somebody from our company has been ranked number one almost the entire time. And we build software that helps you make better predictions faster. And that's all you'll hear about DataRobot. That's it. Can anybody tell me who this guy? I'll be very surprised if somebody can tell me who this is. Bob? so has anybody ever used random forests or a classification regression tree? Yeah, Breiman, right? So this is Leo Breiman. He basically, was one of the inventors of those things that probably many of us in this room use. And he wrote a paper in 2001 that really inspired me when I read it like 10 years later. And so it was called The Statistical Modeling in Two Cultures. And it was really an aggressive attack on statisticians who use regression models and only regression models. And at the time, that was the case. People, when somebody was solving a modeling problem, it was almost all regression. So one quote from there was, "If our goal as a field is to use data to solve problems, then we need to move away from exclusive dependence on," he called them data, but what he really meant was regression models, "and adopt a more diverse set of tools." So he was very focused on results, and that's like me. I just want to, I don't care what tool it is, I just want what algorithm it is, I just want to pick what works best for my specific problem. So 14 years later, we've made a lot of progress. Especially in recent years, there's a lot of progress to adoption of the more advanced techniques. But there's still armies of people, mostly in big companies, building regression models manually, taking months to do that. And I still hear the word black box a lot. And so I agree with everything Josh said earlier about the importance of model interpretability. I would argue, though, that even very complicated models can be interpreted using modern techniques. So I went and looked up what black box was, and I really hated the definition that I found, so I came up with my own. It's a phrase people use when they're scared of technology they don't understand and want to keep doing the same thing they've been doing for the last 20 years. I like that definition a lot better. I won't. I'm going to wait. So if you looked carefully at my title slide, you'd see that the black box was actually open, right? And there was a subtle hint that I think black boxes can be open. I think we can actually look inside these black box models and interpret what's going on. So when we're building a predictive model, like, what do we really need to know? What do we really mean to be? What does it mean to be interpretable or transparent? One thing we need to know that the overall performance of the model is going to be really good on out of sample data, right? So you need a proper testing framework, and you need some metrics to measure how good the model is going to be. Another one that's used common in industry, but is less known to kind of upcoming data scientists, or maybe people that use mostly machine learning, is predicted versus actual by variable, because this is a very tedious thing to do. And I'll show you an example of what I mean by that. And the other thing that you really want to know is, how does the model's predictions change as the values of the variables, the input variables, change, right? There's a few other things you might want to know, but really this is it, right? These are the main things that you want to know about the model, regardless of what technique it is, if it's a regression model or if it's a random forest or a neural network. And none of these actually depend on the algorithm you're using, even the third one, which is a surprise for some people. So the number one, out of sample performance, there's plenty of choices there, right? I'm not even going to read any of those, but there's a lot. And for the other two, I'm going to walk through an example of a real problem. This is predicting hospital readmission. And one variable in this model is, so just a little bit more in the use case. Patient comes to the hospital, they get discharged, goal is to predict, will they come back to the hospital in a certain amount of time? And one variable in the model is the number of prior visits to the hospital the patient had. So that's what these blue bars are. Blue bars are the number of rows in the data set that had that value, starting with 0, 1, 2, 3, 4. We can add on here the actual hospital readmission rate. And you can see the more visits to the hospital the patient had in the past, the higher the hospital readmission rate, right? Which makes sense. Now, if you build a predictive model, one thing you can do is you can actually calculate what is the average prediction in each of these buckets. And you can overlay it on the actuals, right? And so I can say, how does my model fit, not only overall with some kind of metric like Gini, but how does my model fit the data on this dimension? And this actually turns out to be important when talking with regulators in some industries. They want to know, are you treating everybody fairly, at least according to the data? And if we look out there, you can see towards the right side, we're actually not doing very well on, I think it's data point 8. And the reason for that, though, it's probably OK, because there's hardly any data there, right? So if the model actually was fitting there, you'd probably actually have a problem, probably be overfitting. Now, what about what's going on inside? This doesn't tell us anything about what's going on inside the model. This is just showing us the average prediction and how it compares to the truth along this dimension. If we built a regression model, we could look at the slope of with the regression coefficient and plot it here, and hopefully we would see a positive slope, and we'd be happy. Okay, it's in the general direction. That's good. But with other models, even like an ensemble or random forest, deep learning, it doesn't matter. The Netflix model that had 200 models in it, any of those models, you can use something called partial dependence. And it's pretty computationally intensive, which is why it's probably hasn't caught on until recently. And this shows like the marginal effect along this variable inside the model of how the model's predictions change as this value of this variable changes. And so you can see that if I'm building a model, I want to get some confidence that my model is doing right by this dimension. I can look at this and I can see, yeah, it's following along nicely with the actuals. The other nice thing about this is that it's nonlinear too. So if we were building a regression model, we would have been forced to try to fit a line to this. So again, that can be done regardless of the method you use. By the way, if you want to learn more about partial dependence, this is where I first learned about it. Since there's some variations of it, you can Google and you can find a lot of literature out there, but this is probably one of the best examples. So actually, just a note on this book. I love this book so much that I would use it in interviews. So when somebody would come in for an interview, I would ask them, if you had to go on a desert island and do modeling consulting for the rest of your life, and you could bring one book, what would it be? Because that's a very realistic scenario. And if they didn't pick this one, then I would kind of like, knock them off a few points. So if once you convince people that you can actually interpret these black boxes, and by the way, when I say people, I mean maybe statisticians or people that are obsessed with regression models. Once you educate them on this, the next thing that comes out of their mouth is compliance. Oh, we can't use it because the regulators or compliance or this, right? And so I went out and looked at the definition of compliance because I didn't understand what they were talking about. I didn't like that definition either. I like this one. A word people use as a last resort to defend the status quo after they realize that their 100-variable regression model is an arbitrary representation of reality that is less accurate, robust, and interpretable than the modern alternatives. That's what I think. So I probably just pissed off some people here. If not, then the people who watch this online, they'll be pissed off about that. It's okay. Yeah, no thumbs down on YouTube. Yeah. So just to give example, like what I meant here by arbitrary representation of reality. Let's say 3 statisticians go into a bar and they're kind of getting drunk, and one of them wants to have another drink, and the other 2 are like, no, we shouldn't. We've had it enough already. It's really dangerous. We're probably going to get in a car accident and die on the way home. And so they decide to go download some data to figure out who's right. And so they download this data set that has accidents and different variables and whether or not there was a fatality. And the first statistician builds a model, and he comes to the conclusion, and alcohol involved. That's what they're interested in here. Does alcohol impact the probability of fatality? One of them builds a regression model and comes up with the following conclusion. Looks like as long as we use seatbelts and don't roll over, we'll survive. Having alcohol in the system doesn't make much difference. Notice the low coefficient there for alcohol involved. Second guy, he also builds a regression model. And he says, looks like drinking and driving leads to fatal crashes. Probably shouldn't have another drink. Also, the later the better, so we should wait here until midnight. Notice the high coefficient there for alcohol involved, right? Which is saying that it's kind of arguing with the first one. And then the third guy builds a model, and he puts opening door, is police officer, booster seat in use. And he's like, no, we just need to wear our lap shoulder belts and our booster seats and be police officers, and we'll be fine. Oh, by the way, my model has a lower log loss, so it's right? So. Okay. All right. And just another kind of crazy example of a regression model. This is called the killer potato. This is kind of a famous example. On the x-axis is the total yearly potato production in the United States. On the y-axis is the total yearly potato. It's the total number of homicides in the United States. Clearly, there's a cause and effect relationship there. So the point there is, even if your coefficients, even if you do have some significant coefficients, it doesn't really mean that it's representing what's really going on. By the way, that example comes from a book called Exploring Data by Ron Pearson. Really good book. Okay, do I have time for the unicorn? Let me see if I can fit this in. Okay, so let me tell you the punchline, since I don't have too much time. The punchline is this. There's a shortage of data scientists. I'm going to tell you how that shortage is going to be solved. I'm going to try to do it in 1 minute. So this is our standard definition of data scientists. Thank you, Drew Conway. There's hacking skills, which is what we call programming, which is the ability to write programs to get data, manipulate data, explore data, build models, implement models, right? There's math and stats, which you have to have a foundation, but you also have to know about the algorithms, and you have to have some practical knowledge about applying predictive analytics. And then the domain knowledge, of course, understanding the business and understanding the data, right? So this is our definition of a data scientist, and there's our unicorn. The current data science education goes like this. You learn statistics, you learn programming, algorithms. You got to learn all that stuff before you start to learn like how to apply it and do something useful. And so if you look at if you think about like how the number of students that drop off during one of these different parts of the data science education, somebody studying statistics for a year or two, a lot of them are going to drop off. Somebody trying to learn to program, you're going to lose a lot of them. Looking at the internals of algorithms, going to lose all of them. So by the time they get to the point where they start to actually, apply some of what they've learned, you've lost a lot of the students. So there's not that many left. And the ability, if you look at the ability to tackle a real-world problem as a function of time, you can see that you really don't. Not until you have all these, and you start actually learning the practical knowledge, can you actually do something useful. So here's a better way, and here's how the data scientist shortage will get solved. This stuff here will be, for a large part, automated. And education will start at the practical knowledge, a more pragmatic version of data science education. And you can immediately become useful. And that doesn't mean that statistics and programming and algorithms, it's not valuable. But it can happen afterwards. So you can become immediately useful, relying on some of the more modern techniques, and you can actually solve some problems. And then you can go deeper, as deep as you want to do, as deep as you're capable of, and be able to solve more problems and probably solve problems even better. So I think that so my takeaway is there's technique-agnostic ways to look inside models and interpret models. And the shortage of data scientists will be solved by a combination of pragmatic education, practical education, and tools that automate the modeling process and automate data science to levels which are right now probably most of us in the room think are impossible. Okay. And I'm out of time.
Great, thanks, Jeremy. It's terrific. But the punchline, I mean, to tie it a bit, you talk to what you guys actually do. So this concept of multiple models that apply to different types of situations. So you guys basically enable the automation of choosing the right model for the right data, right, or the right problem. Do you want to talk about this since you
talk about what we do? Okay.
Yes.
Sure.
Since again, like the other guys, you kindly did not turn this into a product pitch, which we always appreciate.
Yeah. So we make it very easy for people to build highly accurate predictive models and deploy the models. So we basically, somebody uploads a data set and tells us what they want to predict. And we try hundreds or thousands of different combinations of pre-processing, feature engineering, data cleansing, variable selection, combined with algorithms, all in parallel, all open source stuff, almost all open source stuff. So we'll compete algorithms from R, from Python, from H2O, Spark, and just kind of compete them all against each other and see what works best for yours, right? So, then you can deploy any of those. At a core of our application is a Kaggle-style leaderboard, where all the solutions kind of get ranked by the metric that you choose. And you really. When we do a sales pitch, what we do is we walk into a company and I say, we have no slides, we have no marketing. I'm just going to show you the demo. That's it. That's how we sell our product.
Not a bad way when it works. Cool. Time for like one or two questions.
Hi. Oh, smells. I was just wondering, have you used DataRobot on Kaggle, like for a Kaggle competition? And I was just wondering what happened.
Yeah, yeah, we have. So a couple examples. First of all, some Kaggle competitions require, to pull a bunch of data sets together and a bunch of stuff that only humans can do. But there was a Liberty Mutual competition about a year ago predicting fire losses for insurance. And we came in first, but that was a combination of DataRobot and some of our data scientists. But what was more impressive is we actually, one of our advisors, who's not a data scientist, knows nothing about insurance, he came in 5th place. And this is out of 600-something people, including 30-something Liberty Mutual employees that have competed. I think on average, the Liberty Mutual employees came in 290th place out of 600. And actually, more recently, if you look at, there's a Kaggle competition right now, which is HomeSite is running a Kaggle competition right now. I think the robot is in 3rd place right now. It's under somebody named Sergey Jurgensen, who's one of our data scientists, but he's really just using DataRobot and clicking buttons. Yeah.
This is very cool. One more.
It won't always win. I mean, but.
Hi. Question. There's probably some conventional wisdom about what algorithms are best suited to certain classes of problems. People probably tend to pigeonhole and categorize that way. But based on what you do, I'm wondering if you have any really interesting, surprising, funny examples of where the exact opposite algorithm from what you would have expected turned out to be most suitable for a certain problem. Right.
I guess every time it's not deep learning, people are surprised these days, right? Because that's the answer for everything. I don't have any particular examples where something was very surprising. I'll say that gradient boosted trees tends to be the one of the top algorithms, like 40+% of the time, and I think. More often than not, it's an ensemble that's the best. So what our software does, once it runs the individual models, it'll automatically try different ensembles of them together, and those also end up on models. So those typically end up being the best. One very surprising thing is we tried something. We tried to build a regression model that used information from all the models that have been run before. It just as kind of a crazy idea, and now it turns out to be like one of the best models that like almost every time. It's like we call it DataRobot Prime. That was pretty surprising how well that worked.
Okay, wonderful. So since we're getting seconds away from the pizza and the beer, I want to use the opportunity to say a big thank you to our speakers, but also a big thank you to mostly our speakers who were wonderful tonight. But also to Bloomberg for once again hosting us, to Ed over there who does all those videos that you guys can find on YouTube on our channel, and like all the FirstMark folks as well, Andrew here, Ty, and thanks to you guys for coming once again. Really appreciate it.